2025, and we've just read Du Bois' thesis, and we are convinced of existence of matter waves. So naturally, we are looking for a wave equation for matter. And for matter part, we know analytical mechanics. And for the wave part, we have a kind of tension between our views. One view is coming from our already classical view. The other is what has just Du Bois given us. So I try to synthesize these two views. And classically, a wave is a smooth function that satisfies the wave equation. That's the best definition I can think of. And the other one, which is just we learned by Du Bois, is wave-particle duality, which involves frequency. So essentially, it is about frequency. So as I said, there is a tension. The classical wave equation knows no frequency. It's any function that satisfies the wave equation, but Du Bois has just said that frequency is essential. So what do we do to reconcile these two views? Well, naturally, because we've just learned about Du Bois, we are excited about quantum mechanics. We will try to prefer having Du Bois as our principle, as our guiding principle. So we would naturally try, we say if a law of nature is telling us frequency is important, then so be it. And we will enforce all waves to acquire frequency. And the other view is, which is not barely explored, is to say two is incomplete. Frequency, not all waves have frequency. But let us first go enforcing all waves to acquire frequency, which is naturally we take the solution of the classical wave equation and try to find frequency using calculus. Now, right now, we solve for k, and there are three possibilities, none of which can be distinguished theoretically. The first one is, of course, we promote k to an operator, as just in orthodox quantum mechanics, and everything after, almost everything after in the history. The other two possibilities, B and C, B was given by Schrödinger in a different context and not this explicitly. It was in the gauge transformations. And C is what I want to explore. And it is very important to emphasize that at this stage, without any presumptions or experiments to guide us, there is nothing, no theoretical argument can be given to refute any of these. So all of them equally must be pursued and considered. So let us first consider Schrödinger's gauge, the Schrödinger's definition. Schrödinger tried to transform the wave function of quantum mechanics into a real one because of his philosophical preferences. And so coupled to the Dirac equation or Klein-Gordon equation, there is a gauge transformation of the four potential that changes wave function to a real one, which is Schrödinger did not give it as a new definition of wave vector or momentum, quantum mechanical momentum, but we can see that using our old gauge connection, we can actually arrive to what Schrödinger proposed. So this is about Schrödinger's gauge. And then I want to show that both the operatorial definition, orthodox quantum mechanics, and Schrödinger's definition are special cases of the third possibility, which is rather easy to see. We take the polar representation of the wave function and find the guiding equation. We see that operatorial definition gives us gradient of the phase, also Schrödinger's definition, but not the third possibility, which gives us a new term. So as far as I know, this new term has not been considered. We see, therefore, that there is some more information in the wave function. And actually, this demonstration makes one think of the Bohmian mechanics. in which we are taking, if you see here, we are taking just the real part. We throw away the imaginary part of the first possibility, first line here. So Bohmian mechanics comes very close to this, but throws away the real part. There are several arguments for this. One of them is velocity has to be a real number, which is not that satisfactory. The other using the continuity equation, probability conservation, which comes from the Schrödinger equation. And the other argument is using the CPT invariance. Using CPT, one says we have time reversal, and in time reversal, wave function changes to its conjugate. But we have to see that all of these are based, all of this CPT, the proof of the CPT theorem is, based on the operatorial definition. The whole history of quantum mechanics has been based on the operatorial definition. CPT theorem in its proof requires unitarity, which I will now show that it does not hold for what I propose. So if we substitute my definition in the relativistic energy conservation, we get a nonlinear Lorentz invariant wave equation, which rather looks like Klein-Gordon equation, but it's not. And the relation to violation of unitarity and nonlinearity comes when we consider the condition under which this equation simplifies to Klein-Gordon equation. And the condition turns out to be the incompressibility of the Madelung fluid. You know that we can think of Schrödinger equation as governing the evolution of fluid of probability, quantum hydrodynamics. And in fact, if we impose this condition, the vanishing of the divergence of the momentum or velocity, we get the Klein-Gordon equation. So again, we see that Klein-Gordon equation is a special case. Madelung fluid is incompressible. But for this nonlinear equation, it can be compressible. Now, how does it relate to violation of unitarity? Well, very simply, the new term goes to the right-hand side of the continuity equation, and it accounts for generation of probabilities. We have to take, of course, the complex number, so we have to take its modulus. So this will show us the rate of generation of probability. So unitarity no longer holds. So more about this violation of unitarity, I have to say, it has also consequences for the Hilbert space, because Hilbert space is a vector space, which means linearity, and it is also an inner product space, which is needed for inner product for unitarity and adjoints. But again, both of these are not true in general. For the new term in the guiding equation, changes all of these. So we no longer have unitarity and linearity. So a very important question arises now, we tend to think that Hilbert space and our understanding of quantum mechanics are fundamentally intertwined. So this is an important point that is brought up here. And also because uncertainty relies on our operatorial definition of momentum. Again, it is hard to see the status of uncertainty with this new definition. So we are talking about uncertainty, and alarms are rising now that, well, it has been proven experimentally, there is no doubt about it. But philosophers of physics know better that it's not that simple. One possibility is that we have a certain regime in which the fluid of probability, if we can ever continue to talk about probability itself, because I will come to that on the role of Born rule. One is to say, in a regime where the fluid of probability is incompressible, we can talk about uncertainty. The other is that we just don't go experiment uncertainty principle in itself without any theory. So it's not that simple. So there are some very critical questions arising here, which I do not intend to go in detail to them, but these are prospects for future inquiry. As I said, Born rule and the measurement problem. A statement of the Born rule is that a square of modulus of wave function give us the probability of a superposed quantum state collapsing into a single eigenvalue. So we have superposition and we have eigenvalue. Superposition is about linearity, and eigenvalue, which is related to linearity, is about operators. But for this, our equation is no longer an eigenvalue problem. As you can see, this nonlinear equation is no longer an eigenvalue problem. So Born rule itself becomes vague and blurred by this new proposal. So it may be possible that we have to look for a new meaning of the wave function, and that brings me to the second possibility. Recall that in the beginning I talked about another possibility, to say that de Broglie relation is incomplete. So this brings me to this possibility, and I want to consider the second possibility. The second possibility starts by saying that not always are harmonic, not always are monochromatic. No, in fact, our definition, classical definition of a wave, has nothing to do with frequency. So, looking differently, we have mathematically, frequency is defined by a Fourier basis of the wave of the function space of wave functions, L2, as a Fourier basis. So it seems that our law is depending on the choice of basis, E equals h bar omega. The usual reply to this is that, well, we work with this, but it is always possible in principle to, at the end, take an inverse Fourier transform and state our results in terms of energy as a function of time. But that's not the case. Evidently, this equation, the inverse Fourier transform, is divergent. So this has to be correct. How do we correct this? My proposal is via a principle of maximum frequency, which is very similar to the principle of maximum velocity of special relativity. And also, I want to bring back the notion of rotation related to spin, because we are thought that in quantum mechanics, it's no longer possible to think of spin as a rotating tiny particle. But I want to, for a moment, consider that possibility also. So, how do we implement this principle of maximum frequency mathematically? We need a function that is has a bounded domain, so that we can have frequencies in a range, have a maximum and a minimum, and it has a good inverse Fourier transform. Well, for a bounded domain, there are two possibilities in the elementary functions. One of them is square root, and the other is logarithm. But logarithm does not allow for minimum itself to be a curve. So that's simply, I take this as a good argument that this function must be actually the form of the gamma factor of a special relativity, whose inverse Fourier transform is just the Bessel function. So using these altogether, I correct energy relation, Einstein-de Broglie relation, and then it is possible to take inverse Fourier transform of energy and state it as a function of time. The inverse Fourier transform is no longer divergent. This this inverse Fourier transform and this whole implementation of principle of maximum frequency brings a new notion of locality. Now, in analogy, it is very simply, we can think of a new metric, which gives us the factor here. It is completely analogous to a special relativity. But we have to bring back our notion of rotation and angles related to spin. So this new notion, we have a new notion of locality and a new metric. And this new notion of locality, it is very interesting that this locality is independent of locality in space-time. So let us call this new space angles time space. And locality in this space is completely independent from locality in space-time. And actually, again, analogous to special relativity, we can have cases depending on the sign of the line element. So this offers a possibility of considering entanglement as a possibility of explanation of entanglement, because it is saying that two rotating particles, again, I'm bringing back that picture, two rotating particles which have a close enough angle, close enough is determined by the metric, which have a close enough angle can be correlated. And again, there is no sign of any distance in space-time. So this offers a possibility for entanglement, and using the old definition of frequency as time derivative of angles, and on the other hand, definition of frequency as gradient of the logarithm of the wave function, we can state angles as an integral of the wave function. So this shows us that wave function, because it is a function on space-time, but on the other hand, two complex numbers, wave function can be considered as a bridge between angles time space and space-time space. So in conclusion, in the first part, I pointed that there is serious contingency in our very foundations of quantum mechanics. You know, it is thought that we have a very clear definition of momentum, and everything is then about Hilbert space and commutativity, etc. But as much as I can see, there is no theoretical argument for that can distinguish any of these definitions. That was the first part, and this contingency is very important for us. And we also see in the first part that the most general possibility to which both Schrodinger's definition of momentum and operatorial definition using the guiding wave are special cases. And in the last part, I came to the conclusion that there is a good possibility that we can explain, not explain well, but at least try to explain entanglement using this new notion of locality. Well, I think now I'm finished, and if there are any questions, I would be glad. or if there is any part that I should re-explain or any vague. Thank you.
Thank you, Alireza. We have time for questions. Are there any questions? That does not seem to be the case.
Yes.
In which case we have now 9-minute break and we will reconvene at 11:30 with Paul Neger's talk.
Thank you.
Okay, thank you.